Hello students, welcome to the lecture series of synchronous and induction machine. Today in this lecture we are going to see about the CO3. See, the CO3 is interpret the construction, types, losses, efficiency, parameters and applications of three-phase induction motor. In our offline classes we have discussed about the construction, types of induction motor, and we have derived the torque equation for induction motor and starting torque, all those things. Here in this lecture we are going to explain the torque production in induction machines and analyze the various factors associated with torque in induction machines. So already in the previous session, that is in the offline class, we have completed the torque production and its equation, and then starting torque and the condition for maximum starting torque, all those things. By knowing that, you can do some characteristics curve, that is called the slip torque or speed torque characteristics of induction motor. Yes, in this session the outline is slip torque characteristics or speed torque characteristics of an induction motor, and there are various regions marked in the slip torque curve or speed torque curve. And then speed torque curve for change of R2 meaning that rotor resistance for different rotor resistance, right? Let's see the figure here, which is showing the speed torque curve of induction motor, typical speed torque curve. Here you could find the speed which is in the x-axis, the rotation speed in percentage. It is taken as percentage. It is taken as percentage. It is in x-axis, and in the y-axis we have taken the torque. And when you plot a curve between these two, that is the torque versus speed, it will be look like this. Typical torque speed characteristics of an induction motor, three-phase induction motor. See that full load torque, we are naming it as T, capital T. And if you check at the time of starting, what is the torque? It is approximately 1.5 times of full load torque in squirrel cage induction motors. So only at the time of zero speed, see that zero speed is at the time of starting. So while starting, the torque will be somewhere at 1.5 times of actual torque, that is the full load torque. See, the capital T is the full load torque and 1.5 times of capital T will be the starting torque. And here you could see the pull up torque, and we have breakdown torque, that may be 2.5 times of full load torque. This breakup torque we will get at the time of applying braking. So this N can be of rotor speed or synchronous speed, anything you can take it. So here in this figure we have the figure A and B, which shows the actual speed torque curve of an induction motor. Say it is 0 to somewhere 1000 rpm plus, and The torque values are from 45, 75, 150 Newton meters. See that the region here, you could find a region. This region, it will act as motor, whereas the region it becomes generator, and somewhere region is there, that is braking region. So in the same induction motor, if you change the frequency, see that if this curve is for the 60 hertz for 40 volt, whereas in the other case, if you are increasing the voltage to 660 volt and increasing the frequency to some other value which is 90 hertz, you are increasing voltage as well as frequency, then the curve, the speed torque curve is moved. And if you reduce the frequency and voltage also, there is a change in torque and speed curve shapes. See, when you are reducing frequencies, right, when you are reducing frequencies, your motoring region is limited. Obviously, when you are reducing the frequency, the speed will be reduced. So within that speed, from 0 to within that rated speed, you can operate your machine as motor. And the starting torque can be improved when you reduce the voltage and frequency. See that at the time of 0 speed, that is at the time of starting, we can get more torque comparing with the higher frequencies. So that may be noted. Whereas in this picture, it will shows the complete speed torque of induction motor. There are three different regions: the low slip region, and then medium slip region and high slip region. All those things, based on the three different modes of operation is happening. In generator mode, see that if the speed is greater than the synchronous speed, and it goes up to double times of synchronous speed, meaning that if you take NS as 1500 and this will be 3000, right, 2 NS. So the 1500 to 3000, it will work as generator, and 0 to 1500 it will work as motor, right, and minus 0 to minus negative speed minus 1500, which acts as a braking region. So the power flow, see that power flow, the P1 maybe the input power, and PM is the mechanical power developed. In between there are different powers. Those things were denoted with different notations, that is PCS, PF, PCR, PW. These are all the power losses happening in stator and rotor side, right? The P1 is the input power, P2 is the input power to rotor, and PM is the actual output power from the motor, mechanical power developed. In between the losses are core losses, vintage losses, and copper losses. There are different losses associated in machines, in induction motor. So that losses we will discuss in the other chapter, other session. So see that in motoring mode, we have all the power stages. So the torque and speed are in the same direction. Torque and speed are in the same direction. Say it may be in the clockwise direction. If you say C, it will be like clockwise direction. So whereas in the other case, if you want to make it as braking mode, the speed is reversed. The torque is in the same direction, but the speed is reversed. So only here the power, mechanical power, is in opposite direction to the of motoring, and remaining things are same. You are braking, you are suddenly stopping. It is like plugging, the electric braking used in motors. Plugging. How the plugging is done in induction motors? Simple. When it is running, you just interchange any two lines of stator. Usually we have RYP connected with the induction motor. In that RYP, if you change any two, R and Y, or Y and B, or R and B, then it tends to reverse. So when it is suddenly happens, there will be some braking torque available. That braking torque is enough for stop the machine suddenly. So it reverses its direction, so that we have shown here the N is in opposite direction. Say in the motoring mode, if it is clockwise, here in the braking mode it will be anti-clockwise. Coming to the other mode of operation, that is generator. In generator, you know very well that is mechanical to electrical. So this type of generators, we call it as induction generators or asynchronous generators. Note that it is asynchronous generators or induction generators. When you are operating induction motors above the rated speed, it can be worked as generators. Instead of motoring, it becomes generating. It has mechanical input power and electrical output power. It is totally reversed, but the losses associated is same, right? We have the stator, rotor. In all the stator, rotor, we have got the copper loss, core loss, vintage loss, all those things, but the power flow is reversed. See that the torque is reversed, the speed is same direction, but the torque is reversed from the motoring mode. So three different modes of operation. For all those modes, here in this picture we have shown the speed torque curve. Instead of speed torque, you can also draw the slip torque. Speed and slip are same, right? If the slip is 0, the speed is rated. If the slip is 1, the speed is 0. That is the difference. That is reverse, vice versa. See, if you are putting speed as 0, then the slip is 1. You know slip is equal to ns minus nr, synchronous speed minus rotor speed. So ns minus nr equal to 0, then slip is equal to 1. So when speed is increasing, the slip is decreasing. And if the speed is ns, meaning that ns minus ns, nr is equal to ns, that will not be the case in real time. We know that it should be lesser than the synchronous speed always. It never catch up the synchronous speed, stator speed. But the ns in theoretical case, if it is ns, then it is 0, slip is equal to 0. At the time there is no torque. Now you can understand, when it is running at ns, there will not be a torque. And when it goes beyond ns, then your slip becomes less than 0, that is slip becomes negative. Whereas in the other case, if it is negative slip, the generating action takes place, and if you are making the slip which is greater than 1, then it becomes breaking region. So this happens in the negative, ns minus of minus, so plus, so it will be greater than 1. In the negative speed, opposite direction of rotation, you will get some slip which is greater than 1, whereas in this case it is less than 0. So this is the area where we are operating induction machine system motor. So this is speed, this one is the slip. So you can write the slip values for 3 different regions. When S is less than 0, generating region. When S is greater than 1, it is breaking region. And for motoring, it is greater than 0 and less than 1. Greater than 0 and less than 1. Next, in this picture, in this figure, you can see the same slip torque or speed torque characteristics, where the rotor resistance is varied. You know, in the previous slides, I have shown you things for different voltage and frequency, whereas here I am just showing you with the different different rotor resistance, that is R2 dash. See that. So when you are increasing R2 dash, you could understood that the starting torque is improved. So only we are using the wound rotor slip ring type of induction motors, which will give you higher starting torque when you add resistance with the rotor at the time of starting initially. So when you are increasing the rotor resistance, you can improve the starting torque, right? That is evident from this figure. Yes, that's all about the slip torque or speed torque characteristics of induction motor. Thank you.